In this video, we're going to cover section 3.2 using second derivatives to find maxes and mins in sketch graphs. So in section 3.1, we did pretty much the same thing using first derivative information. So in this section, we're going to learn how to use the second derivative instead of the first. So our objectives here will be to classify the relative extrema, meaning maxes and mins of a function, using the second derivative test, and then apply continuous functions in a manner that shows concavity. So we'll learn what that word means here in just a little bit. All right, so our first definition, is what it means to be considered concave up versus concave down. So suppose that f is a function whose derivative f prime exists at every point on the open interval I. Then the function f is concave up on I if f prime is increasing. In other words, that the slope of the tangent line is getting bigger. So in a picture like this, so say over here you have the slope of the tangent line, over here which would indicate a negative value, and then it slowly moves across here, and if you were to draw your tangent line in, eventually it turns to positive. It goes from negative, then it hits 0 at some spot here, and then it's positive, so it's getting bigger as you follow your graph left to right. That shows the shape that we consider to be concave up. Think of it like a bowl, like it would hold water on the inside. F is concave down on an interval I if the derivative, meaning slope of the tangent line, is decreasing. So in this case, if I drew a tangent line on a point here, it's a positive, it hits 0, and then it turns negative the further I go. So it's getting smaller in value in terms of the slope. So if I move left to right, if that's happening all the way through, that f prime is decreasing, meaning the slope of the tangent line is getting smaller, that gives me a concave down shape. Think of this like an umbrella. Like if you poured water on it, it would fall over the top. So concave up is like a bowl, concave down is an umbrella. All right, so what does that mean in terms of second derivatives? Well, if the first derivative is increasing, that means its derivative must be positive. So the derivative of the first derivative is the second derivative. So this is called our test for concavity. If the second derivative is positive, that would mean that the first derivative is increasing. Second derivative positive means the graph's going to be a concave up shape. Second derivative negative, meaning the derivative of the first derivative is negative, means it's decreasing. So second derivative negative means the shape of the graph is concave down. So if you can tell the shape of concavity versus or being concave up versus concave down based on if your second derivative is positive or negative at a particular point. All right, so when we're using it to determine the relative extreme values, meaning maxes or mins, suppose that f is differentiable for every x in an open interval a to b, and there's a critical value c in that interval for which f prime of c was 0. So we found a critical point that was found by setting the derivative to 0. So the function f of c, or that y value of the graph, is a relative min if the second derivative at c is greater than 0. Let's think about why. We just said that the second derivative being greater than 0 means concave up, like the bowl, right? So if my critical point was plugged in, that would be your min, right? Your bowl shape means you'd have a minimum. So second derivative at c positive, we have a min. The function f of c is a relative max if the second derivative evaluated at c is less than 0, meaning negative. So second derivative negative means concave down. That's the umbrella shape, upside down, which would mean at the top of that would be your max, right, if it's falling down on both sides. So setting the second derivative equal to 0, the first derivative test can be used to decide whether or not that solution is a relative extrema. Let me go back to that again here. So what this means is f prime greater than 0 means you have a min. F prime less than 0 means you have a max. If f prime equaled 0, this would not tell us anything. It's not greater or less than 0, so then you'd have to use the way we did it in 3.1, meaning does it increase to decrease or vice versa. All right, so let's try an example. Graph the function given by f of x equals x cubed plus 3x squared minus 9x minus 13, and then find the relative extrema. All right, so let's find both our first and second derivative. So first derivative, 3x squared plus 6x minus 9. Second derivative then is 6x plus 6. All right, solve, take your first derivative set to 0 to get the critical values. So that first derivative set to 0, we divided everything by 3, then factor, then set each factor to 0, and then solve, and we get -3 and 1. So those are the critical values. So use the first derivative to identify the critical values, and instead of then doing the chart with the increase to decrease or decrease to increase, we're just going to use our second derivative instead. So -3 and -1 are the critical values, or -3 and +1. So now we're going to plug those into our second derivative. So our second derivative function that we found, plugging in -3 gives me a negative number. So if it's less than 0, that means concave down. Think of the concave down shape, meaning the umbrella. That would mean a max. When I plug in 1 into my second derivative, we get 12, which is a positive number, meaning greater than 0. Second derivative positive, concave up. The concave up shape was the bowl, meaning you'd have a min. This is a lot more, when the second derivative is easy to find, like it is on a polynomial function, this is much faster than going through the whole interval chart that we did in the first section. All right, and then all you have to do now is find the function values at each critical point. So plug them into f. So you got here an ordered pair. From -3, you get 14, and if you plug 1 into f, you get -18. So you have -3, 14 was your maximum, and then the 1, -18 ordered pair is your min. Right? So then to go to the graphing step from there, by calculating and plotting a few more points or using your calculator, you could verify. So what we know without the calculator from the work we did, -3, 14 was a relative max. So we could plot that point and know it looks like this because it was a max and we were concave down. And then you can plot 1, -18, and knowing it's a min or concave up. And then just plotting a few extra points then can fill in the rest. All right, so let's try another example. You can try this one on your own if you like. Just pause the video, see if you can go through the same steps on your own, and then press play to see if you did things correctly. All right, first and second derivatives, or we need to find those first. So first derivative would be 30x squared minus 30x to the fourth. Then the second derivative, 60x minus 120x cubed. All right, solve, setting the first derivative to 0 to get your critical values. First derivative set to 0. We can factor out a 30x squared. And if you set to 0, this gives you 0. And then if you set 1 minus x squared equal to 0, you get both plus and minus 1. So the critical values, by plugging each of these x's back into the original function g, would give you the ordered pairs 0, 0, 1, 4, -1, -4. We're going to use our second derivative test with those critical values to see if they're maxes or mins. So the second derivative, when you plug in 0, gives you 0. So that means it's inconclusive, right? It's not positive or negative. So and this is a case where you'll have to use the first derivative test to show that there is no extrema. So if you did your chart with first derivative values like we did in 3.1, you would see that there's no sign change, and that would lead to no extreme value. Plugging a 1 into my second derivative, this gives me a negative number. I don't really care what the number is. If you can tell it's negative, that's really all that matters. It's less than 0. That means concave down. So upside down umbrella means you have a max. And when you plug -1 in to your second derivative, you would get a positive number, something greater than 0. So positive second derivative means concave up, which is the bowl. That would give you a min. So you have a relative max at the ordered pair 1, 4, and a relative min at the ordered pair -1, -4. And then graphing the function would give you verify those results. At -1, -4, down here is your min. 0 was neither. And you could have just figured that out from looking up the graph also. And then 1, 4 is your max. All right, theorem 6, finding what we call points of inflection. So if a function f has a point of inflection, it must occur at a point x naught or x sub 0, where the second derivative at that point either equals 0 or the second derivative does not exist. Okay, so if you found your second derivative set to 0 or found out where it doesn't exist, those are possible places for points of inflection. The point of inflection means it's going to change concavity. It's going to change from being concave up to concave down, from concave down to concave up. All right, so determine the points of inflection for the function given by, this was the last example that we just did. All right, so we're going to use theorem 6. So if a function has a point of inflection, it must occur where this happens. That's what theorem 6 says. So we're going to take our second derivative of this and solve for our x naught values. So second derivative set to 0 and showing that there is a sign change of the second derivative on either side, meaning if the second derivative changes sign, it changes from being concave up to concave down, or vice versa. So find what g double prime is and then where it equals 0. So if this is g, the second derivative is the derivative of the first. So that's the first derivative. Then we're going to take its derivative. So your second derivative is 60x minus 120x cubed. So we can factor out 60x, leaving 1 minus 2x squared. And then you can set to 0. So if you set 60x to 0, you get 0. And if you set 1 minus 2x squared equal to 0, you would get the square root of 2 over 2. So setting this to 0 would be 1 equals 2x squared, so 1/2 is x squared. So x squared is plus or minus 1 over square root of 2. They've just rationalized it. So 0 coming from this solution plugged into the function gives me 0. If you plug in square root of 2 over 2 back in, you get 2.475. And if you plug in your negative square root of 2 over 2, you get negative 2.475. So those are your ordered pairs. All right, so the strategy for sketching graphs. All right, step 1, derivatives in domain. Find both first and second derivative, noting the domain of the function. Okay, meaning what values of x are you allowed to consider. Part B, critical values of f. Find the critical values by setting the first derivative to 0 or noting where it does not exist, and then find function values at those points. So plug those back into your original function f. Determine increasing and decreasing to find your relative extrema. So substitute each critical value from your step B back into the second derivative to apply your second derivative test to know if it's concave up or down at the critical points. That'll tell you if those are maxes or mins. Determine candidates for inflection points by setting your second derivative to 0 or doesn't exist. Evaluate your function at those points. And then use your candidates for your inflection points to define intervals using relative extrema from step B to determine where it's concave up and concave down. And then from that, you should be able to sketch a graph by calculating extra points as needed or verify that all that information lines up with what your graph on the calculator shows you. All right, so we're going to go through this next example by pretty much doing all of those things. So find the relative extreme of the function and sketch the graph. All right, so here is our function, x cubed minus 3x plus 2. Part A, derivatives and domain. First derivative, 3x squared minus 3. Second derivative is 6x. The domain is all real numbers for all of this. So you don't have to worry about not being allowed to use certain x values. Next is critical values of f. First derivative set to 0 gives me 3x squared equals 3, or x squared equals 1, so x is plus or minus 1. My possible places for maxes and mins are at plus or minus 1. So plugging those back into f gives me the ordered pairs, negative 1, 4, and 1, 0. All right, increasing, decreasing, relative extrema, we're going to plug those critical values into the second derivative, because that was the quicker way. So second derivative evaluated at negative 1 is a negative number. That's less than 0. So at that point, negative 1, 4, a second derivative being less than 0 means concave down, the umbrella, means you have a max. And if that's the case, if it's concave down with the umbrella, it would have to be increasing on the left and decreasing on the right. So it's concave down at that point, and then because of the concave down shape, increasing on the left, decreasing on the right. Instead of trying to memorize all the details here, it is very helpful to understand the basics. Like if I look at this and go, I know that the second derivative being less than 0 means concave down, I just think of the shape. And once I think of that shape, I know that means a max because of the shape. It means I have to be increasing on the left and decreasing on the right because of the shape, not because I memorized all those other things. All right, second derivative at 1 is 6, which is greater than 0. So second derivative being greater than 0 means concave up. So we should have a minimum at the ordered pair. It should be decreasing on the left, increasing on the right. So 1, 0 is the min, decreasing on the left, increasing on the right, and it's also concave up at the point because your second derivative is positive. So all of this information is gathered just by knowing second derivative greater than 0 means that what the shape looks like. All right, inflection points. Set the second derivative to 0. Solving that gives me 0. So f of 0 would be 2. That's the ordered pair. And then concavity. From step C, we conclude that f is concave down on the interval, negative infinity to 0, and concave up from 0 to infinity. We talked about that when we did step C on using shape. And then using all that to sketch the graph. Okay, again, graph on your calculator if it's faster, then we should be able to go through all of your information. Negative 1, 4, we said was a relative max, which it is. 0, 2 is the inflection point. Noticing it's concave down on the left and concave up on the right. That's a concavity change point. 1, 0 is the relative min. Right? Increase, decrease, increase, like it's noting down here. And then concave down, right, like we said over here, and concave up. Now they plotted points to get that, but you could also graph that on your calculator and just make sure all that makes sense. All right, let's try another one. Relative max and min of this function and sketch the graph. Derivatives and domain. First derivative. Second derivative. All real numbers again. Any polynomial function has an all real number domain. Critical values. First derivative set to 0. Factor out of 4x. Set each to 0. Plus or minus 2. They should have also listed an x equals 0 here, which they do next, but they should have brought that down. So x equals 0 comes from this. So 0, 1, 217, and negative 217. So you should have 0, 2, and negative 2. All right, increasing or decreasing relative extrema. So the second derivative at 0 is 16, greater than 0. It's positive, means concave up. So we'd have a min, and then it would decrease on the left and increase on the right. So 0, 1 is a relative min, decreasing on the left, increasing on the right. And notice on the left of 0, they're bounded by this negative 2, and on the right, positive 2, because those were the other two critical points. So think of the number line. If it helps to maybe draw the number line and plot your 3 critical points so you know what the endpoints of your intervals look like for increasing and decreasing. And then we said concave up, right, because of positive second derivative. Second derivative at 2, we get a negative number. Becomes 16 minus 48, that's clearly negative. So a negative second derivative means concave down. It's going to give you a max, which is going to be increase on the left, decrease on the right. So 217 is a max, increases on the left, decreases on the right. Concave down at that point. Plugging in negative 2, also less than 0, second derivative. So again, concave down. So it's another max, increases on the left, decreases on the right, and it's concave down. Inflection points come from setting your second derivative to 0. So if I'm solving that equation, we get plus or minus 2 square root of 3 over 3. If it was rationalized, this is square rooting both sides here, gives me 2 over root 3. They've just rationalized that. That's about 1.15. So F is concave down between negative infinity and negative 1.15, and between 1.15 and infinity, and it's concave up in the middle. Again, if you draw the number line and have plotted the points like we did in section 1, those points land this point, right? The negative 1.15 lands in one of those intervals. The positive lands in another one, right? And then that's where we get these endpoints from, right? Based on your second derivative information. All right, and then your graph from the calculator should verify. We said negative 217 was a max, 0, 1 was a min, positive 217 was a max. Inflection points were at negative 1.15, so about right here, which makes sense. Concave down on the left, about right there is where it switches to being concave up, and then about the 1.15 right here, right, it would be concave down on the left and concave up on the left and concave down on the right. Where inflection points indicate a change in concavity. All right, so here's our summary. Second derivative determines concavity. Second derivative positive greater than 0 means the graph's concave up. That's the bowl. Second derivative less than 0 or negative means graph is concave down. That's the umbrella. If C is a critical value and the second derivative is positive, meaning it's concave up, then F of that critical value is a min. The bowl shape has a min in the middle, like an opening upward parabola. And if C is a critical value and the second derivative at C is, this should say less than, this is the wrong way here, this should say less than 0, then F of C is a relative max, meaning it's concave down, which would give you the maximum. If C is a critical value and the second derivative equals 0, you have to use the first derivative to classify it as a max or a min. If the second derivative at x naught equals 0 or doesn't exist, then you will have a change in concavity to the left and the right. And there's a change in concavity. So you find the possible places where that could happen by setting second derivative, either 0 or doesn't exist. If there's a change in concavity, meaning you have a change in sign of your second derivative, then we call that an inflection point. So finding extrema, intervals over which it's increasing, decreasing, intervals of upward or downward concavity, and points of inflection is all a strategy for accurate curve sketching. So before graphing calculators existed, this is a way to accurately go through all of the process of drawing a complete perfect graph. All right, that is the end of section 3.2. I know there's a lot of new information, and these are very time-consuming problems and a lot of steps to remember. So please reach out if you need help or would like to meet with me to go over the details of how these problems work. All right, and that is then the end of section 3.2.